Let's continue our conversation about intermolecular forces, which are the forces that hold molecules together or not, right? If the force is weak. And that determines the state, whether something is a gas, a liquid, or a solid, and also the boiling points, solubility, and other so-called colligative properties, which we will discuss in this chapter. Here's an example of three molecules that have various molecular weights. And so the molecular weight here listed in this row here has a little bit to do with the intermolecular forces, but it's related to the weakest intermolecular force referred to as the London dispersion force. And so we should not focus on that when we are determining the state of the matter here, right? So for example, we have xenon gas, and xenon gas has a molar mass of 131 grams per mole, and just because it's higher than that of propane and water doesn't make it a solid or a liquid. In fact, it is a gas. All right, so what is it that makes these things stick together? And that we look at polarity of the bonds as review, electronegativity, which you learned early in one of the early chapters when we discussed the periodic table and periodic trends, is the ability of an element to draw electron density towards it. And so if we look at the one with the highest value here, fluorine, and take note that the noble gases are cut off here because they don't have any electronegativity value because they have a full valence shell and they no longer need electron density. But fluorine, as you know, has 7 valence electrons. It's one away from fulfilling the octet rule or filling up its valence shell. So it is very eager, so to speak. Of course, elements are not eager, but it does have the ability to draw electron density towards it, and so it gets the highest value. And it's also closest to the core, right? And the core has the positive charge in it. And so there's only a couple of little shells, whereas chlorine, of course, there are more electrons packed between the core and the outer electrons. So the value of electronegativity actually decreases within a group. And that's true if you look not just at the noble gases here, I'm sorry, at the halogens, fluorine and chlorine, but there is that drastic drop between the second and the third period. This is again all review, and so we do. This is listed as decrease towards the left, but you can also simply say that increases towards fluorine. That's how you remember. Fluorine is the highest. Everything either decreases towards it or I'm sorry, increases towards it or decreases away from it, which means if you look at the carbon group, you're going down, that's going to be a decrease in electronegativity. If you're going down this row, and it's not quite right because the transition metals are an oddball, but we'll discuss this at a different time. And so we have an increase in electronegativity within a period here. And so you can this is for sure true for the main group elements. And that's the most important part when we're discussing covalent compounds anyway, because we're looking at nonmetal interactions. Hydrogen is hovering over here. Of course, the periodic table has it there because of its valence shell. But as far as electronegativity is concerned, it really fits in as a value of 2.1. And it's shaded here in pink, so it has a fairly high electronegativity. It fits in between boron and carbon, and you would do well to memorize where it fits in. That will help you determine whether a bond is polar or nonpolar. And so if you, for example, have a carbon-hydrogen bond, what you do is you look at the difference in electronegativity. And the difference, 2.1 and 2.5, is 0.4. So that's essentially a nonpolar bond. So carbon-carbon bonds, difference is 0, and carbon-hydrogen bonds is 0.4. The difference isn't strong enough to create a pull of electron density towards another. Because what will happen is if you have let's say you have oxygen and carbon, right? So oxygen, carbon, now the difference is larger than 0, but smaller than 2. And so you have a rather large difference in electronegativity, and you have a polar bond. What happens to the electron density is pulled towards the more electronegative element. And that's how you create a dipole, okay? But it also translates into what type of bonding we have, right? So we have nonmetals binding to each other. We make a covalent bond. We are sharing electrons. And if one of the elements is more electronegative than the other, you have electrons that are being pulled, electron cloud in the bond, right? If you have a oxygen hydrogen, which is one of the strongest uh, polar bonds, and in fact, this is the one that you probably remember engages in hydrogen bonding. Hydrogen bonding is a very strong polar bond, and it gets its own name because it involves hydrogen. It's very common, and it's very strong. And so the line here, of course, is an electron cloud, and so the electron density is pulled towards oxygen, and so the yellow region here is more negative, as is indicated here, and the blue region is more positive, and that's how you create a dipole, and then positive and negative ends can stick to each other and build a three-dimensional network, and that leads, of course, to either liquefaction or solidification. Now, if the difference in electronegativity is rather large between two elements, especially if you have a metal and a nonmetal, that uh, that electronegative element is so strong compared to the metal, which is very weak. In fact, if you look at the periodic table and you look at the metals over here, you see that they have very low electronegativities. And if you look at or consider the electron shell, there's only, for lithium has one electron, and if you remove that, it has a full valence shell or a noble gas electron configuration. So it really wants to get rid of those electrons, right? So that's what will happen here. You have complete removal. Basically, this electron is completely removed if the strength is large, and we get then an ionic bond, cations and anions. But we do want to focus on covalent bonds here, and so keep that in mind as we go through the different intermolecular forces. This is the one you probably remember. Here we have two water molecules. And so the oxygen to hydrogen bond distance here measured in picometers is 96 picometers. That's an intramolecular force. It's a covalent bond. It's a strong bond, and if it's strong, it makes it shorter. And the intermolecular distance between non-bonding oxygen and hydrogen here, which is the red dotted line, you have to subtract the 300 from the 296, is 204 picometers. So that's quite a bit longer. It's almost twice as long, but nevertheless, there is an interaction there. So we have this dipole, and for an intermolecular force, a force between atoms, non-bonding molecules or atoms of non-bonding molecules, it's actually fairly strong, right? So that's just as a reminder, and we always indicate that dipole by putting small deltas, so it's a partial negative charge and a partial positive charge. Okay, and so this is called the hydrogen bond, but we want to start out with the lowest intermolecular force. The weakest one is called the London dispersion force. So why does something like iodine, which is this, iodine is dimolecular, and the difference in electronegativity between two iodine centers is 0, of course, so it's a nonpolar covalent bond, but it is a solid. So that must mean that iodines are sticking together. And that is due to the weakest intermolecular force called the London dispersion force, right? And that is due to the electrons that are moving around, right? So you have an electron shell, you have different orbitals. Here we're just looking at an s orbital. It's easy to look at, but they can also be, if you recall, in d orbitals and p orbitals, different path. But nevertheless, they go around an atom very quickly, or a molecule, and so they move, right? And if you slow that movement down, or if you have a rather large molar mass of a nonpolar covalent molecule, then you have several electrons, And so you have the possibility that for a brief moment, like here we have the two electrons that are shown far apart, but they're starting to be somewhat towards each other. Here they're completely on opposite ends. And of course, this is freezing it in time. They go very fast. And then here we have a fraction of a moment or a short period of time where both electrons are to the left. And so if now this bumps into another atom that is, by the way, this is helium here. You can tell by the core there are two neutrons and two protons there, and there are two electrons. So this is helium gas. And if you cool down the temperature, you can actually liquefy helium. We can obtain liquid helium here. And so what we're doing is we're slowing down the movement of the electrons. And then for a brief moment, two of these distorted dipoles, induced dipoles is what we call that, bump into each other, and then they just stick, and then they can build a network. But you've got to cool this down, especially for helium, to get an induced dipole, right? So that is the weakest, and these are completely non-polar molecules where this occurs. And so looking at the group 8, where we've already said the electronegativities of those elements is 0, or there is no value attached with these noble gases. But the boiling point, and this is in Kelvin, so all of those are gases, right? So these are in Kelvin. If you wanted to contrast that to Celsius, this would be negative 269. Right? You just take the 4.2 and you subtract 273 degrees Celsius, and then the one with the highest one is still negative 108 degrees Celsius. But so we have larger molecular weight, we have more electrons, more movement, so the chance of getting an induced dipole is higher for higher molecular weights. As I mentioned before, iodine is a solid and also nonpolar, but iodine has a molar mass of 254 grams per mole. If you think of this in terms of electrons, helium, as we mentioned, has a molar mass of 4. There are 2 electrons here. Fluorine has 18 electrons, and iodine is 106 electrons. So you've got 106 electrons that are all hovering around, and so the chances of you getting an induced dipole are much, much higher. So it is actually a solid at room temperature with a melting point here of 113.7. And so you can argue that as you increase molar mass, you increase the London dispersion forces. That becomes really interesting if you're looking at alkanes. Now, alkanes are saturated, meaning there are no double bonds, carbon-carbon, and carbon-hydrogen containing compound. And although they can be branched differently, so those are alkanes here. Here's a double bond, so this is no longer an alkane, but it's still a hydrocarbon. And so if you look at them, they are completely nonpolar. Carbon-carbon bonds have a difference in electronegativity of 0. Carbon-hydrogens is 0.4, so they're considered nonpolar. And they're all gases, right? But they do have an increase in boiling point going from methane. Oh, wait a minute. We have pentane here. Of course, that's a liquid, actually. So here you see the impact of the intermolecular forces, an increase in molar mass, more electrons are moving around. All right, so what did I want to draw here? Oh, yeah, I know. I wanted to show you these molecules. Okay, so here we have pentane and neopentane, which they both have the same formula. They both are C5H12. They're just connected differently. They're called isomers. You will learn a lot more about this when you take organic chemistry. But so they have the same molar mass, but they have drastically different boiling points, right? So pentane has a higher boiling point than neopentane, and that's because it has more surface area. It can pack tighter here. You see, this is just long and has rather large surface area. So a second one can come in and pack tightly, and another one over here. And so they can just pack very tightly and therefore have a higher boiling point and melting point. Neopentane has less surface area considered, because it's packed tighter. You wanted to draw it out. It looks like this because you've just learned how to draw Lewis structures. Maybe it'd be useful to look at that. But this is neopentane. Okay. And so you have to remember that this center here is tetrahedral. So it does really look like a sphere when you look at the ball and stick, or the space filling model as we have here. So this is not flat, of course. This is a tetrahedron. The angles are 109.5 degrees, and so there's less contact area, and so this one it zigzags up and down. Hopefully you remember some of the line structures. They're called line structures, what I just did there. This is actually pentane. So each corner has a carbon. This will become important, and you know that carbon needs 4 bonds, so each of these carbons also has a hydrogen attached to it. And that's how it wiggles, and so it can pack a lot tighter, and so it has an effect on the boiling point, right? So essentially more surface area. Same molar mass, but different boiling points. So again, this is just small area of interaction, large area of interaction. So I didn't need to draw this. I guess I have a pretty good picture for this. All right, let's just move along. Let's look at all of the alkanes that are straight chain. Right, these are not branched. All we're doing is we're increasing the carbon count, and there's a beautiful linear relationship between molar mass and boiling point here. Look how linear that is. So for every CH2, that's essentially what you're doing here. Going from 5 to 6, you're adding a CH2 group here, right? So if you have ethane, which is just C2H6, you go to the you add a carbon to it, you're essentially adding a CH2 group every time. So going from 5 to 6 is adding one CH2 group, right? And so you go from 5, 6, 7, 8, 9, you've got the same increase in boiling point, right? As long as they are connected in a straight chain like this, right? The minute you branch them, as was the case in the neopentane, you no longer have a linear relationship. So here we are looking at the straight chain alkanes, starting with the most simplest one here, which has 1 carbon. So that would just be CH4, right? And then, 10 carbons would be C10. And then how do you know how many carbons there are? Well, I'll show you a little trick. It might be useful when you move on to organic. If you have 10 carbons in a row, that means you have to have 10 CH2 groups that are connected. So for every carbon that's connected, you have twice as many. So if we say that the number of carbons is n, you have 2 times n hydrogens, which in the case of 10 would be 20. But then you also have to cap off the ends. So there are going to be 2 hydrogens that will cap off the ends. So it's going to be 2n plus 2. That formula will give you the number of hydrogens. So this would be C10H22, right? And so here in purple, we have the melting point, and this blue line here is of course the room temperature. So at room temperature, when you hit 17, that's when you have a solid, right? So and then the boiling point, of course, is higher of these as well, so you have to stick in. And so here are like these 4 here are actually gases at room temperature, and then right there you have a liquid. And then everything from 5 to 16 here is going to be a liquid. So this range here is going to be a liquid, but we should really be looking at that, because right there is when we hit the solid, so it's 17. And so we actually make use of that when we separate the crude oil, right? So all the sources of these hydrocarbons, and they're not all straight chain, but for the most part, we use that. We have big distilleries in the south, in the Houston and Lake Charles, Louisiana area, where they have these distilleries. These towers here that you're looking at are 100 yards or taller. So this is quite a distance, and we can do this on a small scale in the laboratory. We can separate certain hydrocarbons. Uh, but so the one with the highest boiling point is going to go up the highest in this distillation tower, right? So you have these little glass rods or chambers here. I forgot they have a name, but this is where it can start condensing, and so the ones with the highest boiling point, they need the most energy input, and they will not go as high, and so they come off at lower ends, right? So you can collect the different, depending on their molar mass, you can collect them at the different stages of that distillation tower. So we are using this information, and then you can further distribute or separate these compounds. All right, so I'm going to pause, and when I come back, we're going to look at the second intermolecular force called the dipole-dipole moment.